Hey everybody, welcome to Module 8 of NT160. This is going to be Reactor Plant Materials Part 2. So we're going to be talking about thermal stress fundamentals. So you got to understand the difference between an ordinary temperature change, like things change temperature all the time. I got my coffee cup this morning. It's got hot coffee in it. I'm able to put hot water in it, and there's initially the cup is cool, but as time goes on, the outside of the cup gets warmer and warmer and warmer, and that temperature change happens throughout the cup. So you got to understand the difference between that temperature change and thermal stresses that are going on when I am adding hot coffee to a cool cup. So any material can heat up and expand or cool down and contract without much trouble if it's free to move. And what we have here as an example is if I have thermal stress on a wall. So let's say I have a wall here and I've got some temperature source over here. I got some heat source out here, right? The thermal stress happens when there is expansion or contraction that has resistance. And what I mean is if I have heat here, and this is atmospheric, so this is my coffee cup, and this is just 70 degrees Fahrenheit, and I put hot coffee in that's at a perfect 192 degrees Fahrenheit. That's the temperature you make your coffee at. There's a temperature difference, right? That delta T. So that temperature change by itself isn't enough to create thermal stress. The materials have to be restricted. And what that means is different parts of the material have to change temperature at different rates for thermal stress. So you have to have a temperature difference. Got that. You also have to have you have to understand the coefficient of thermal expansion for that material. And so you have to understand what that coefficient is, what that resistance to temperature transfer is. You also have to understand the modulus of elasticity. Modulus elasticity, let me skip ahead in my notes here. So modulus of elasticity means stiffness. A material with a higher modulus resists stretching or compression more than a material with a low modulus of elasticity. So when you hear modulus of elasticity, think stiffness. If a material is really stiff, it tends to resist stretching and compression. If it has more elasticity to it, it allows for more stretching and compression. So materials with the higher modulus of elasticity develop greater thermal stresses. So it's stiffer material. It's less resistant to that change. So it develops greater thermal stress because it resists elastic deformation more strongly. If the material is fully restrained, so that expansion or contraction. So as I heat this up, this material here is expanding. Right? It's expanding outward. It's expanding laterally. It is expanding a little bit this way, but not much. Most of the time, materials will expand in their longest plane. And so it's expanding this way. If the cup has a really high modulus of elasticity, really high stiffness, then this is resisting that expansion. And so you develop stress as the inside of the cup tries to expand and the outside of the cup tries not to expand until that temperature change, that difference in temperature, I didn't realize that was below delta T, until this evens out and this temperature is slowly transferred through all the layers. And then you have similar temperatures on the inside and the outside. Okay. So if the material is fully restrained, right? The thermal stress relationship is based on the modulus or stiffness. It's based on the thermal expansion coefficient. I should write these down for you. Modulus of elasticity, modulus, I'll just write modulus, which is stiffness. And then it's based on thermal expansion coefficient, and it's also based on the temperature difference, that delta T. This is why large temperature changes, right? That large temperature changes across a restrained component, a restrained material, something that has a high resistance, like metal, like the metals we use in our nuclear power plants, right? In our reactor pressure vessels. The idea is more restraint is a bigger temperature change is more stress. So when you think about our reactor pressure vessel, that's a lot of stress when we're going from cold plant conditions to starting up the reactor to getting the inside of the reactor really hot. When we have to allow all that temperature to leak through to the outsides to minimize that stress. So the big idea is more restraint, bigger temperature, plus bigger temperature change is more stress. All right, let's pause here for a question. Now let's talk about thermal shock and why rapid cooling is usually worse than rapid heating. So once again, we've got our material, we've got a delta T. So I've got something hot out here, all right? And I've got something, this is, let's say, atmospheric. And so thermal shock is caused by the rapid temperature change that creates excessive thermal stress. It's caused by the sudden addition of hot coffee into my cool little coffee cup. When we have that maximum delta T, that means the maximum delta T is the delta T is greater, then we have maximum stress. It's our biggest difference in stress across the material. And when I say across the material, it's because one part of the material changes temperature faster than another part. So the outer layer responds first. We saw this, I'll use red here. This outer layer responds first, and then the inside lags behind. So this temperature, this heat is moving into the material layer by layer by layer. And when we had that initial temperature difference, that was the greatest stress. But as this moves in and moves across, and in this heat, the temperature is getting conducted across. The heat is getting conducted across. Then we slowly remove that large amount of stress. But the point here is the outer layer responds first and the inside lags behind, and that mismatch creates the largest amount of internal stress. So during the rapid heating, that surface heats first, tries to expand. We need to understand what the resistance is. When we started off with this outer layer here, this heated first, and all this interior space is trying to resist that contraction. That puts this surface layer that's heating up in compression and the interior in tension. Why is the outside in compression? Jason, didn't you mean expansion? No, I meant compression. Because it's trying to expand. What's a way to imagine putting a balloon in a box, and a small box? You take a small box and you put an empty balloon in it, and then you blow up the balloon. And the balloon is trying to expand, so there's an expansive force being applied, just like the heat's trying to expand that outer surface. But because the box is the resistance, right? The box is resisting that expansion. That puts the balloon in compression. The more pressure I add, the more compression the balloon experiences. Is that analogy check? I think it does. That was off the top of my head. All right. So during rapid cooling, let me write this down, getting ahead of myself. So during heating, surface is in compression. So what happens when we have rapid cooling? Well, the surface cools and contracts, but the hotter interior resists that contraction. And so we had two things we talked about in heating: tension and compression. So just know, no matter what, whether you're heating or cooling, you're only dealing with those two components, tension and compression. So when we're heating, the surface that's being heated is in compression and the interior is in tension. That tension is that resistance to the change. But in cooling, the surface cools and contracts first. The hotter interior is resisting that contraction. That puts the surface in tension and the interior in compression. It's the same thing reversed. So you're in either compression or tension. And if you're cooling, the surface is in tension. So rapid cooling is more dangerous. Materials are generally, you just have to file this away. Just here's a fact, understand this, file it away forever. Materials are generally weaker in tension than in compression. They're weaker in tension. This is especially important in thick-walled components like reactor vessels, which is what we're dealing with, because the inside and outside don't change temperature at the same rate. The thicker the component, the easier it is to create a severe temperature gradient. So rapid heating, got my eraser on. Rapid heating is surface compression and the interior tension, whereas our rapid cooling is surface tension. I don't know if you can even read that, and interior compression. All right. Rapid cooling is worse. That's so much more important. That's the big thing to take away. And what gives us those different temperature gradients? Like, what are the things that affect how bad that is? Thicker walls are bigger temperature gradients. If I have a thin wall here, my temperature gradient, right? I have the same delta T, but the gradient is that delta T, that change in temperature across a thickness. And so if I have a delta T of a specific amount, let's say 100 degrees Fahrenheit, across this distance, that is a shorter temperature grade than across this distance. And so that bigger temperature gradient is one of our challenges. Well, let's pause here for a question. All right. In this section, we're going to talk about thermal shock resistance and some material properties. Not all materials respond the same way to thermal shock. The reason they use ceramic for a coffee mug is because of how well it responds to that thermal shock. And that thermal shock resistance depends on several different properties. The important ones that we're going to talk about in this module is tensile strength, thermal conductivity, how well it conducts heat throughout the thickness of the material, the coefficient of thermal expansion, and elastic modulus. Remember what elastic modulus was? Basically the stiffness, and then the ductility. Now that should be something you remember from a previous module, right? Ductility. Apparently I can't write and spell ductility at the same time. So our materials with high thermal conductivity usually resist thermal shock better. Ceramic transfers heat very well. Ceramic has a high thermal conductivity, so it resists that thermal shock. It spreads the heat pretty quickly. If you take your hand on the outside of an empty coffee cup and you start pouring hot coffee in, you feel that heat right away. It's transferring through there fast. It has a high thermal conductivity. That's what helps it resist. That's one of the things on our list that helps it resist that thermal shock. It spreads heat more quickly. Materials with a low coefficient of thermal expansion are better. So high thermal conductivity, low coefficient of thermal expansion, because they change size less for any given temperature change. And what that means is some metals expand really rapidly. Some metals don't expand as rapidly. In fact, if you remember way back, have we covered that yet? Bimetallic temperature indicators. We take two metals with two strips of metal with different thermal conductivity values, low coefficient of thermal expansion and a high coefficient of thermal expansion. And we solder them together, and then we put them in a little curl. And what happens is, as temperature changes, one metal expands more than the other, and it puts deflection on it. If it's in a coil, it tends to straighten out. And so that idea is that even across metals and different materials, there are low coefficients of thermal expansion and higher. And the low coefficient of thermal expansion is better because it's the outside surface of the reactor or the inside surface of the reactor is not trying to expand as much with that temperature change. So ductility, high ductility helps. Well, why? Well, remember what ductility was. It's its ability to deform without a permanent change. So a ductile material can change shape a little bit, change length, change, width as it expands without being permanent. So the high ductility helps the material deform without cracking. It allows that stretching without cracking. Lower modulus of elasticity also helps because the material can accommodate more strain with less stress. Yeah. So if a material spreads heat well, expands less, and can deform more before failure, it handles thermal shock better. That was a mouthful. All right, let's pause here for a question. All right, in this section, we're talking about thermal fatigue and things that we do to reduce damage. Thermal fatigue is different from one thermal shock event to another. And thermal fatigue is also different from one large thermal shock event. Thermal fatigue is failure caused by repeated cycles of thermal stress. What's a good example? Over time, if sometimes you get a cheap coffee cup, right? And you use it and you use it and you're using it 3 times a day for a couple of years. And one day you're looking at it and you're like, why are these little cracks in it? Why are those cracks happening? Well, because it was a cheaper ceramic. And that thermal fatigue is starting to set in. It's failure caused by repeated cycles of thermal stress. So even though ceramic is a good material, even though ceramic conducts that heat through the wall of the cup very well, very easily, continued repeated cycles of that adds lifetime stress to that component, that cup. So a component like a reactor pressure vessel may survive one cycle, but that repeated startup, shutdown, heat up and cool down cycle can eventually initiate cracks. Those cracks start to grow and it leads to failure. This is why they've engineered that, or calculated, engineers have calculated that a reactor pressure vessel at normal operating pressures and temperatures, so you've been operating at 100% power for 6 months, a year, year and a half, and all of a sudden something happens and you have to depressurize that reactor, that rate of cool down is so extreme that there's so much thermal fatigue involved, it's going to initiate problems, and you only get one cycle like that. And so, what we try and do is we try and control those heat up and cool down cycles. We try and control that pressure addition and pressure release so that we have, as long as you're controlling them, you have more uniform temperature distribution. You're avoiding the sudden thermal shocks like the cold water. Have you ever made coffee and you just got done with making a pot of coffee and you go to wash it and you turn on the sink and you haven't let the water heat up and you just put cold water on it? That's the one instance. That is the sudden cool down event. It can't handle that. But if you can slowly heat it up, you can slowly cool it down, minimize that temperature difference, and wash your carafe over and over and over. But eventually they fail. So anyway, what do we do? What do we do in our reactor vessel? So we preheat our feed water using feed water heaters. We also have pressure temperature limits. And we have graphs and operational procedures to control our heat up rates and our cool down rates. And we have to live by those pretty strongly. So if you get a question asking what helps prevent thermal stress damage, usually it's some form of controlled temperature change rather than sudden temperature change. That makes sense, right? We want to control it. We want to slowly add heat. We want to let that heat transfer through the material. We want to slowly add pressure, let that pressure pressure doesn't transfer through the material. But I think you understand what I'm saying. So the thermal fatigue, the repeated thermal cycles cause crack initiation, crack growth, and eventual failure. So we reduce that damage by controlled heat up, controlled cool down, uniform temperatures, and avoid sudden transients. That ADS system firing off is a sudden transient. One rapid depressurization and the reactor pressure vessel is done. All right, let's pause here for a question. And let's talk about brittle fracture, ductile fracture, and cleavage, because that's kind of the what I keep talking about with the ADS event, the rapid sudden depressurization of the reactor vessel, is the brittle fracture concerns. So what is brittle fracture? Brittle fracture is sudden catastrophic failure with little or no plastic deformation. So there is a lot of examples. World War II taught us a lot about brittle fracture, unfortunately. A couple dozen ships cracked in half. Like one of the best examples was right down here on the Columbia River in Portland, the SS Schenectady. It cracked almost completely in half just while sitting dockside, 1943, sitting dockside on the Columbia River near Portland. And that temperature difference, it, the existing flaws from the material and the low toughness let a crack just rip right through the vessel. And once a crack starts, it propagates pretty quickly. Think of your windshield, right? This is brittle fracture is what happens to a rock hits your windshield. Now you've got a defect. And as that temperature change happens, the sun, and you got the AC on the inside, you got this hot sun on the outside, and that temperature difference, that stress, that strain, that pushing, that expansive difference on the inside and the outside of the window propagates that crack, lets it take off right across the window. And all it takes is you just have to reach up and touch it. Just touch that crack on the windshield and whoop, right across. That's brittle fracture. So these happen with very little warning. These cracks propagate rapidly. The component can fail suddenly. Ductile fracture is different. Ductile materials deform significantly before failure. They absorb more energy and they give more warning. What's a good example of that? Like something where you're trying to, you're bending it, and then it takes a lot of that bending. There's a lot of ductile transformation happening before it fails. I can't think of a good example. I was thinking like one of those rubber school erasers, but I don't know. Brittle fracture is just rapid crack propagation, low energy absorption. There's not a lot of ductile bending going on, like a cracker. Cracks, right? Brittle fracture. Whereas a cookie, I brought in, that's what I was going to do. I brought in a couple of cookies to use as examples of the ductile versus brittle. And then as I was setting up, I ate them. So anyway, one common brittle fracture mode is cleavage fracture. Cleavage fracture is just the cracking of a material along specific atomic planes in the crystal structure with very little plastic deformation. So it's just a mode of brittle fracture. If I have a material and I start putting forces on either end and there's something here that it's balanced on, if it's ductile, right, it'll take a bend in it before a crack propagates, before the crack starts and goes through. But cleavage fracture is as I'm adding that force, it's just a failure mode where it just cracks. But how does it know where to crack? Well, that's the cleavage fracture. It's just fracturing along that atomic crystal structure. So we talked about like BCC, FCC, all these different types of atomic structures, right? And this is the FCC where there's atoms in each plane. Well, there's an atom, there's one there, and then there's one here. And so cleavage is just shearing at those joinings of the atoms, that crystal structure at the atomic level. So I don't know. Don't get too hung up on cleavage fracture. It's just a rapid, sudden. It's not tearing molecule or atoms apart. It's fracturing along those atomic crystal structures. All right, let's look at, now that I've drawn on my face, let's look at Sharpie V-notch. Sharpie V-notch, right? You're going to hear that word, especially if you're an operator. It's an impact test. A Sharpie V-notch test is just where you take a metal sample. So I've got my metal here, and I put a little V in that metal, and then I strike it by a swinging pendulum so that we have a controlled, continuous, same amount of energy. And so I guess I should have drawn that vertical. So imagine this, let's just draw vertical, put a V in it. And then over here, I've got a big pendulum swinging, and it swings into the material. So this is used to measure impact toughness, the amount of energy a material can absorb before fracturing. So they're going to be looking at this structure right here. And what they want to see is they strike this with a swinging pendulum. The energy is absorbed before the fracture is measured as impact toughness. The test is commonly used to evaluate ductile to brittle transition behavior as temperature decreases. So they'll change the temperature of the material in the environment as they do this. They'll have it in a warm environment, and they'll cool it and cool it and cool it, and they'll strike it and strike it. And so that evaluates that ductile to brittle transition behavior. And they're looking for, do we have plastic deformation? Is this just bending down and no crack? Is there a crack that happens? At what point does the crack happen? Because eventually that crack's going to happen. So you'll have a brittle fracture with either little or no plastic deformation, rapid crack propagation, or you'll have ductile fracture, more deformation, more energy absorption, more warning. And so the idea is that with cleavage fracture is brittle fracture. And the Sharpie test measures impact toughness, how how the temperature affects and how much energy can it absorb before it experiences that cleavage fracture. Let's pause here for a question. All right, let's talk about stress concentrations and fracture toughness. Brittle fracture starts at a flaw or a discontinuity. There has to be something wrong in this metal. Sometimes it's near the surface, sometimes it's inside. Like if I have just a tiny little, we'll draw something red. We'll call that our flaw. Brittle fracture starts at a flaw or discontinuity. So as I have, let's say, expansion on the outside, which puts the outside surface under compression, because it's trying to expand the outside surface, and this is all tensile, this flaw is where that brittle fracture will start. Stress concentrations are localized increases in stress caused by cracks, holes. So if I have a little crack in here or a hole, sharp corners, weld defects. This is why welding is, welders learn so much about materials and how they behave under temperature changes and how to do good welds, because welders can unintentionally add flaws to the metal that then become problems when we are subjecting the material to this compressive stresses under heat up on the outside and the tensile stress on the inside, and et cetera, et cetera. The point is, all these flaws act as initiation points where local stress becomes higher than the average stress on the component. The local stress right here is higher than the average stress. So that's why fracture toughness matters. Fracture toughness is a material's ability to resist that crack propagation. If fracture toughness is low, this crack is going to happen pretty easy. If fracture toughness is high, the material just resists that crack growth, resists that crack growth better. So if you're asked what property is most important in resisting brittle fracture, hint, fracture toughness is the best answer. If you're asked what commonly creates stress concentrations, like cracks, sharp holes, weld defects, and cracks, right? Those kinds of things are what commonly creates stress concentrations. Let's pause here for a question. All right. So the main ideas, let's get back to this. The main ideas here are thermal stress happens when temperature change is restrained, when there is a resistance to the changes that temperature difference is trying to put on the surface. Thermal shock is damage from rapid temperature change. Rapid cooling is the most severe case. Materials that spread heat well and deform without cracking handle thermal shock better. That repeated thermal cycling causes thermal fatigue. Brittle fracture is dangerous because it is sudden and gives little warning. Stress concentrations, those things throughout the material, make crack initiation more likely. Fracture toughness is the key property that resists crack growth. And then low temperature, and then radiation embrittlement. Yeah, you get that from the material. All right. We have pressure temperature limits to protect the reactor vessel from all these problems. That's Module 8. Thanks.